if there is any work on the material or just testing it or getting some experience with it, then we can definitely go through that at a hack day.
All right, you guys go ahead.
All right, thanks.
Do we have a new location yet for hack days?
No, DAR has been, for the Emacs meetup, has been using Blue Baker, and it's hard to find a place with power and good reliable seating and internet.
And these meet at the office?
Well, I don't know about reserving it on a regular basis and how much hassle you have to go through in terms of think about like what we had to go through at Rackspace, right? It's sort of the same kind of thing that we have. We got to register people and
have you ever done a meetup at the office?
No, but somebody we asked and somebody kind of said there's a little bit of a process about it. So being one of those offices where you're not supposed to bring people in without going through all the steps is kind of annoying. So I was looking at Genuine Joe's on Anderson because they have a meeting room that you can reserve that does have a projector and there's some power and Wi-Fi and things there. So a place like that. But no, we don't actually have a place that we've set that we like yet. So Darb likes the Blue Baker a lot, but the ability to get reliable seating and power is pretty limited. If people didn't have a requirement for power, then if our requirement was only like Wi-Fi and seating, it would be a little bit easier.
Well, just make sure you're charged up when you get there.
Yeah, well, maybe it's not a big deal. In the past, like when we were at Cafe Express, people would often kind of complain that if we weren't sitting near the powers, we'd always try to huddle near the power, and then nobody would use it because they're like, oh, I don't want to take all the power.
Right.
So I don't know. Maybe that's not a big deal. So if
somebody should start a coffee house.
Yeah. There's also, we did our earliest meeting at Monkey Nest on Burnett, and that's a little bit more difficult. It's a smaller of a room, and it's a little bit more difficult to book, and they have a higher requirement of how much stuff you order to reserve it. But it's also a possibility. But people weren't super excited about that, so I don't know what we can do. If you have suggestions, then put them out there because it's worth trying. We haven't done one since Cafe Express closed. We kind of been letting the Emacs group sort of pilot the different locations. All right. Any other Clojure questions? All right. Well, we'll go ahead and get started. I have two things to go through today. One of them is was a question. So last month we were sort of did it as almost as a just an informal meetup with no presentation. And one of the problems that we came into was Sam, who was supposed to be here tonight, had kind of at the end of the meeting tossed up a problem. He had an interesting set of data that he needed to.
Can you make it a little bigger?
Is that not big enough? Could you get better glasses?
How about that? Glasses.
Oh yeah, let me see if we can turn off some of these lights. It always helps to turn off the lights back here. So I'll shut them on. All right. So Sam, this first part was inspired from Sam, who was promised to be here tonight and bring a bigger data set than we had to work with last month. But he's not here, so but I'll still go through it anyways because we've got the material and it's pretty good. He had a data set that he wanted to sort, and it was a set of team records of like these tennis teams that played each other and their scores, and then and if you want to sort something by score, just by like one field, it's pretty easy. But he actually wanted to do this tiebreaker, and he was having some problems writing it. And so we sort of at the end of the meeting we sat down and we wrote this, and I sort of hand waved the last part of the comparator, saying, okay, we've only got a couple minutes left, but it's magic. Just a few more lines of code, it would have all been done. Magic, look how clever this is. And then I said, okay, well, but I'll go work on, I'll go do this, and I'll send you the code the next day, just so we have a complete working thing. And I went home and I started writing, and I realized, oh, this is actually a little bit more complex, because you can't actually mix comparators and value comparisons in Clojure. And so then I was talking with Sam about it. We said, well, this would make a good topic, talking about how comparators work in Clojure, how to write a complex sort, and then how to compose your comparators. Because there's actually not like anything in the core Clojure library for composing a comparator. So that's what I wanted to do now, and I wanted to show sort of what I came up with as what I think should be in the Clojure language for composing comparators, and I'd be interested to get some feedback. But along the way of doing this, I discovered some interesting things, so we thought it would be fun to go into all of this. So we'll start with this. And sorting with in Clojure is pretty easy. We have a function sort, all right? So if we take a list of, so here's a list of numbers. I generated them, I generated them randomly. Nothing magic about these. And we call sort, and it sorts them exactly like we'd expect, right? And in Clojure, we can sort, pretty much anything that's comparable. So we can sort strings, we can sort all sorts of things. How does this work? Well, again, I said we can compare anything that's comparable. So comparable is an actual interface in Clojure, and it all comes down to the compare function. So basically, we can compare anything that we can call the compare function on, right? So we compare. Whoop. What happened there? There we go. I lost my screen for a second. Okay, so we can compare numbers, and when we compare, a comparator is just a function that takes two values and then returns like a standard, -1, 0, 1, or -0, positive, indicating the order of the two elements. So if we compare 1 to 2, we get -1, right? We compare 2 to 1, we get 1, and we compare 2 to 2, and we get 0, right? So anything that implements this interface, we can call compare on, and then we can say sort a collection of those values, right? Strings, same thing. Notice that it's not just -1. Here it's actually H and W, so it's actually subtracting, just subtracting those values. And if it's a negative value, it comes before positive, right? So this is all based upon Java, right? This is the comparable interface in Java, right? Compare uppercase to lowercase, it's a difference of 32, right? So this is our basic ASCII ordering, and two strings that are the same compare like that. One difference here is that we can, in Clojure, we can actually compare nil. So nil comes after or before, right? 1, so that means the nil. Yeah, and then of course we can compare nil to nil. All right, so can we compare something like this, 2 to 2? No, we cannot, because we're not JavaScript, right? Arrays in Clojure. This starts to get into what we were discussing when we were talking about using juxt at the end of the last meeting for sort by. We can compare arrays, and the way we compare arrays or vectors is the shortest array wins. So if you compare an array with 0 elements to an array with 3 elements, then the 0 element one is higher. If you compare one with more elements, then it's higher. So it sorts by length, and then after length it sorts by value. So if it's the same length and all the values are all the comparable values are equal, then it's 0. And here, so here we're comparing, the 1 and 1, 2 and 2, and then 3 is greater than 2. So it compares as a 1, meaning the first one is the larger number. And for the last one, 1, 2, 3, 1, 3, 3. So it's going to compare these, and it's going to compare the 2 and 3, and say 2 is before 3, so we're going to get a -1, right? So this will kind of be important later, because being able to compare a vector of comparable things makes some things like sort by, the sort by that we looked at last month, pretty nice. But there's a lot of stuff we can't compare. We can't compare a list, okay? Because lists are not comparable. We can't compare an object, right, or a map, because maps are not comparable, right? How could we do that? So let's say we have some data like this. This is an array of objects who have score values. Well, we can't sort these because the items in the vector are not comparable, right? So Clojure, the one sort of nice thing that Clojure has on top of this is sort by. So sort by allows us to take a collection and sort it by some function that returns a value. So if I call the function, score on, a map that has the key, it's going to return, in this case, it's going to return 80. So now, if we do sort by, it will sort all of these things by the score value of the object, right, of the hash map. All right. Well, what if we need it in another direction? Well, the key sort by, we could, in addition to taking a key function, it can also take a comparator. Okay. So what's a comparator? Again, the comparator is the function that returns 0, 1, or -1, right? And so we can say get the score value. The value we're sorting by is the score attribute of the object, right? But we're going to sort it descending. Okay, so, and this was an actual sort of an example from the Clojure documentation. Okay, so we sort it by greater than. And it works. And I started looking at this, I'm like, wait, why does this work? Greater than is not a comparator. Greater than is a predicate, right? If we say greater than 2, 1, and 2, 1, right? It returns true. It doesn't return 1 or 0 or -1. Why does this work? This is from the documentation. It makes no sense, right? So this was the first thing I discovered in Clojure that I didn't know, after 5 years of working in Clojure, is every function in Java is a comparator, right? So if I look at less than, right? Less than or greater than, is that a comparator? Yes. Is equals a comparator? Is compare a comparator? Well, of course it should be, because it returns 0, 1, or -1. But what about this function here? Is this a comparator? It is. Everything is. Why? Okay, so here's the magic here. And again, this is your Clojure trivia for the day. So this is a function, which is basically the abstract class that the Clojure I function, or the things that implement function extend from this, and it has this compare method. Compare takes two objects, and it does a little bit of magic, and it figures out, it calls it, and it expects a predicate. It actually takes it as a predicate. It says, is it true or false? And and once it compares it one way, it kind of turns it around and compares it the other way. So that's how it turns like if you think about how would you take greater than and turn it into a -1, 0, 1. You'd say, is it greater than? Yes. Turn it around. Is it less than? If it's greater, and you can by whether it's true or false, it's either 1, 0, or -1, right? By comparing it in both ways. Right? And so that's just sort of built into Clojure. So lesson 1 is anywhere in Clojure where you need a comparator, you can just pass it a predicate. And now, obviously not all predicates are useful for sorting, right? Not all of them. If you call, like ideally, if A is greater than B, it sorts one way, then B would sort less than A, right? Not all true-false things do that, so you have to be careful. But something like less than or greater than does. So that's why anywhere you want a greater than or less than, you can use that. So again, we can call, we can sort like we did here, sort by less than or greater than, right? And we can, you can control both orders by pulling out the value. So that's pretty interesting. What if we have multiple values? So in Sam's particular problem, he had a score, but if the scores were the same, he wanted to apply sort of this tiebreaker function to determine which team is ranked, which team should sort before or after the others, right? So let's say we have a score, and now we have a team name, and we're just going to say like we're going to sort by score, and then if we have two scores that are the same, we're going to sort by number, right? So first thing I want to point out here is that this is a stable sort. So here we have two things that are going to have the same score of 34. One of them's name is white and one of them is green, right? And when we sort by less than, white is before green. And when we sort in the other direction, white is before green. So this is sort of a guarantee of sorting in Clojure, is that if two things compare equally, and we're only comparing score, right? If they compare equally, then they'll be in the order that they are in the original vector. All right. All right. So but we don't, maybe we want green to be before white, right? We want to say, we don't know, but team name is going to be the tiebreaker here, right? So how can we do that? And this is sort of what we started to write last month. So when you're using sort by, a really nice technique is to use juxt. What does juxt do? Juxt, when I call juxt with score and name, it's going to return a function, and that function is basically going to return a vector. Can someone get the door here?
Thank you, sir.
Right, so it's going to return a vector of it's going to call score, the first function on it, and it's going to call the second function that's going to return a vector. Right? So if I call juxt of score and name on score 10, name 1, right? It's going to return a vector. It's going to call the first one and the second one, just like we looked at last time. And as we just saw above, we can compare vectors. When we compare a vector, if the two things have the same length, then it's going to compare the first value as a comparable and the second value as a comparable, right? So if we sort by score and then name, we notice now now green is before white, because in all the other ones it was a stable sort with one value, so white always appeared before green, right? So that works, and that, if you're not too picky about your sort order, this is sufficient for most of what you're doing, right? But let's say, what if when we do this, we no longer have the ability to usefully pass in a comparator like we did before. So what could we do? We can play games with the values. For instance, if we wanted to, so here we're sorting by score, and it sorts its ascending. If we wanted to score descending, well, instead of calling score, we could call negative of the score, right? So 31 becomes negative 31, and then they sort in the other order, right? And so now we have the same, we have score descending, but we still have name ascending, right? Okay, so that works. There's some gotchas with that. For instance, just imagine the range of numbers and signed numbers, inverting them like that. You might have to be aware of your number ranges. But what if we wanted to sort a name descending, right? How would we invert that? I mean, maybe you could go through all the things and subtract 255 from every character from 255, or you could do something like that. But at some point, like there's no natural inverse of a string, right? So this sort of breaks down, but this is the only real way to compose comparators that the Clojure language has. So the next best thing is just to write comparators, right? So let's write some comparators and see, and then I'm going to come back into what I think is the missing abstraction of Clojure comparisons. By the way, Clojure quiz for you. Just think about this. You obviously Java util comparator, right? Compare, right? -1, 1.
And then 0.
Yeah, -1. Sorry, -1, 0.
It's a
1.
Fortran
Yes.
style compare.
Yeah, exactly. Okay, so however, ask yourself, y is greater than, which is a predicate. Sorry. right? Why is that a comparator in Clojure? I just want to twist your mind because I know this is the kind of thing that would drive you crazy. We just talked about it. I'll tell you later.
Wait, okay. Instance, why is it greater than a comparator?
Yeah, a Java util comparator. Because we can use it in place.
Are you asking how or what the motivation was?
How?
Oh. I will have to contact them.
Yeah. It took me like when I was working on this last month, right after the meetup, I just sat at home thinking for like 25 minutes, like, wait, why does this work?
I have a theory.
Okay, go ahead.
Given that we have the capability to tackle the expression problem, I think that they extended the
Function, all functions. If they're a predicate, they're also a job. All functions in Clojure implement comparable, and then they have
all
this
functions?
all functions. Anything anything that's ifun. And here's the implementation in Clojure line A5.
Ah, see, I wasn't gonna. No, that's new to me.
Yeah, I knew
all
you'd appreciate
functions
it.
are comparators.
Yes. Now some of them are not. Some of them, if there's not a Boolean, it's gonna error right. So if you actually try to use it as a comparator, it may error out. And if it's a predicate that is not useful for sorting, if it's not stable, right? If whatever the term is, then
So
it's not useful.
they put in the candy, and some of it might be poison. It's up to us to know what candy to try.
Yeah.
Wow. All right.
Anyways, I thought you'd appreciate that. All right, back to this. All right, so let's write an actual comparator.
I do appreciate it, but yeah, it's a bitter thing.
All right, so instead of doing something like creating the inverse of the value, or this is actually not an inverse. I guess this is just the negative. But although inverse would probably work, right? So we actually want to create a comparison function. So instead of just inverting it, we can do a couple of things. Let's say we had a compare. We could actually write a comparator. It's just called compare in the opposite order, right? That could be our descending, right? So if we have any comparator that we compare that say compares the as we're doing here score, right? Then if we call the second one and compare the second value to the first, that's the comparison in the opposite direction, right? So for example, if we sort by score ascending, right, and we sort by score descending, right, and we're using the same comparison, we're just calling the parameters in the other order. So that's really the primitive that we want to to take something and reverse the sort, rather than playing games, with say subtracting, making the number negative or something like that, right? Okay, so again, considering if we had a compare score here that did one thing, well then my first abstraction is just simply reverse order, right? And this is Java, this is something that the new Java 8 comparison stuff has. In fact, with the exact same name, I discovered. And this reverse order takes a comparator, a compare function, and returns a comparator that, given two values, just compares the second value to the first value. So if we had to compare scores that went in one direction, then sorting with the reverse order of that should return them in the opposite order, right? And the same thing if we had a compare by name, right? If we reversed order a comparison that was using the name, we'd get it in reverse order, right? Very simple. So this doesn't exist in Clojure. You have to write it yourself, as far as I'm aware, every time. Now, second abstraction is compare by, okay? So if we take a value function, so we see sort by takes a value function, right? Well, it sort of implicitly turns that into comparator. If you just provide the function that turns a value into a comparator here, then we can say something like compare by score, right? So compare by takes the value function and calls compare after calling the value function on x and y. This is exactly what you're doing when you use sort by, but if we actually take that abstraction out, out from sort by, just raise it to the top level, we can now say, we can say sort by score, right? So we're going to sort comparing by score, or we're going to sort reverse order comparing by score, right? So that's descending, that's ascending, right? Now that, obviously that's not as clean as just saying sort by score descending, but it's actually something that's extendable. Okay, so the last abstraction I wanted to present, and this is the one I want the kind of feedback on, is what do you do when you still want to take multiple values and compare them? So we said score and then name, or as we'll see in Sam's project, score and then the tiebreaker, right? So let's continue with the name as our first example, because it's a little bit simple. So compare by score then name. We want to wrap this all up into one comparator. It takes two values, x and y. We first compare the score, and then if it's 0, then we return the comparison result of the name, right? This is what you would write. You compare by 1, the first value, and if they're equal, then you go to the tiebreaker value, right? If it's 0, then you call the extra one, right? So if I call sort score by score then name, then we see here again the 34. So all the names are descending, which is notice this is score descending, right? Because we call the second and the first, so the reverse order. And then green before white because the names are being, x and y are being compared to ascending. But that's kind of, this is not really fun code to write, and it's very easy to make a dumb error. And if you have 2 or 3 of those and you wanted to say sort by name and then score, well, then you have to rewrite all the logic. It's a bit of a mess, right? So my abstraction here is compare arrow, right? And this is using an arrow here is probably the wrong name, but I think this is the right abstraction. So it takes any number of comparators, right? And it's basically just doing that same logic, which is to say, take the first comparator, and if it's 0, then call the next comparator. So we won't worry about this code so much, other than just to say, if you call compare arrow with multiple comparators, so our first comparator and then our second comparator, it will call the first one, and if it's less than or greater than according to the first one, it will use that, right? And if it doesn't, it will go to the next comparator, and you can nest, 5, 10, 15. I don't know any use case where you'd want that, but you can have as many comparators as you want in there. So putting all the abstractions together, so we have compare by score and compare by name. So if we sort those, we're going to sort score ascending and then name ascending, right? If we call reverse order of score and compare by name, we should get scores descending and names ascending. Again, green and white, right? If we wanted to sort them both by score descending and then tie breaking by name descending, now we have scores descending and then white and then green for the 34 case. So I thought that, as somebody who's had to do the juxt thing and with multiple arguments, and then get in there and realize I wanted the middle one in the reverse order, this is the abstraction I always wish I had. So how can we use this in a non-trivial case? So here's Sam's data, or this is the data he gave us at the last meetup that he promised he'd give us sort of more data for. But here's 3 teams, and each team has a total number of points, and then they have matches where they played each of the other teams. Okay. Now what Sam wanted, and it was sort of not well defined, but what he wanted to say is if 2 teams have the same score, they get compared by their head-to-head score, right? Now, you can probably see that if you had many teams and you had multiple teams that like if you had 3 teams with the same score and A beat B and B beat C and C beat A, there's no way that this sort makes any particular sense. But ignoring the fact that the way he presented the problem is not really viable, and just say, well, let's run with it anyways. How do we do that, right? Well, clearly, if we wanted to sort this, we can just use a sort by. We can say sort by total points, our data, right? And we can use a comparator. We can say less than or greater than to get ascending or descending. But how would we compare team 1 to team 2 if they had the same points, right? Well, we saw that we could use juxt, and this is what I hand waved at the end of the last meeting. We said, oh yeah, we can just use juxt, but we can't just pull this value out and have a meaningful comparison against the other value, right? That doesn't work. We have to actually use a comparator. But there's no way to put a comparator into that juxt, into the sort by, right?
You have to undergo some sort of value-free transformation and add some other value to those records. That's that head-to-head summary.
Yeah, but even then, so here's the problem, is you need to be able to, if you're comparing team 1 to team 2, if you're using sort by, you need to be able to pull a value out that will compare against the other value without knowing you need to be able to compare pull out your score against team 2 without knowing that you're comparing against team 2, right?
Yeah, okay, all right, now I see what you're saying.
Yeah, this is sort of like
it's a Cartesian coordinate of the two, and you don't know what the
you don't even know which one you're comparing against. So this is sort of what I hand waved at the end and said, like, oh yeah, well, we just have to toss a comparator in there, and then I went, oh, but that actually doesn't work. You actually have to write a full, you can't use sort by at all. You just have to write a full comparator for that. And there's no, again, in Clojure, there's no way to compose these comparators. So, but given our extraction, I can write a comparator like compare head to head, right? So don't worry about the code here so much, which is just to say, this is a comparator that takes two teams, and it will just look at their head-to-head. It takes the full values, and it will just take the team IDs and pull the matches out, and just look at that individual match, right? If team 1 beat team 2, then it compares one way. If team 2 beat team 1, it compares the other way. And if it's a tie, then they're equal, right? So given that we have now that we've written this comparator, which is a lot easier than what we would have had to write last month, we can just compose that. So let's look at some of these. So if I just compare by total points, right, we'll get team 1, team 2, and then team 3, okay? So let's look at their points again. 7, 7, 12, and team 1 is before team 2 because it's a stable sort, right? If we compare in reverse order, we should get 3, 1, 2. Is that what we got here? 3, 3, 1, and 2, right? All right, because that's the reverse with a stable sort, right? We're sorting by points in reverse order, right? But now we can just compose in this head-to-head comparison. So let's say we wanted to sort by total points descending, right? So put the winning team first, and then sort by the head-to-head. So this is basically the reverse of just not doing any reverse orders. Look, I didn't evaluate that function. Hold on. Compare head-to-head. Look. All right, so here, team 3 with the most points is first. Team 2 and team 1, who both have the same number of points. Team 2 beat team 1, so they appear before team 1. All right, and so I think writing a simple comparator like this is, although it's ugly, you have to do that no matter what, because this is a complex comparison. And then with our abstraction of being able to compose these comparators, we can then put these together very cleanly. So I don't know about the names, but this is what I think should be in something to this effect should be in Clojure as a comparison method. Because if you actually have to write this, you're going to end up having to write this compare head-to-head code in the context of this other comparator, right up here, where you're trying to nest these, and there's just no way to put them together. So. after the meeting, if you have any thoughts, or if anybody has any thoughts, or if this scratches an itch, let me know. I'm just kind of curious, maybe I'm the only one that feels this is insufficient, or maybe somebody knows something I don't. All right?
Nothing else, chains, comparators?
Nope, nothing. There are things in the new Java 8, streams and things like that that have new abstractions, but those are extremely difficult to make use of in Clojure. Like the new Java stuff is not easy to call into. All the lambdas and things like that. You'd think it would be a perfect fit, but I'm kind of waiting to see what, if anything, Rich does in the core of Java to kind of make that a little bit nicer. So if we had that, then we could kind of go into some of the Java stuff. In fact, I put a link to some of the how you compose them. Well, anyways, I'll when I post this up, you can, if you're curious what some of the new Java stuff looks like, I can show that. And those are things that might, he might choose to go that route of exposing like platform stuff down. As of today, there's nothing in there. All right, so that was last month's problem, and Sam was supposed to give us some more data so we could actually test it, but you'll have to take my word for it that this simple case is sufficient to show that. All right, so if that wasn't enough, all right, so the other thing we talked about last month, and what I wanted to spend some time on and see how we do, is we wanted to look at some of the pathfinding code, because I think Dar, who's also amazingly not here last night, suggested last month that we talk about how to actually write some of this code. So last month we talked a little bit about advent of code and some of the problems, and how a lot of the problems involved some sort of pathfinding or shortest path. So in particular, we looked at this particular problem, well, let me pull one of the other visualizations up, because that's a little. All right, so for instance, one of the problems from last month, from the advent of code, was a game where you had these little goblins and elves, and they had to, they were basically fighting against each other, and each round, each one of these had to do a pathfinding algorithm. There's like this, the rules specified how it determined which opposing army it was going to try to get closer to, and then run a pathfinding to try to make its best path, and the goblins and elves would come next to each other, and if they were next to each other, they would fight, for example. And this was a very complicated problem, but there were quite a number of advent of code problems where you essentially have some sort of a map, some sort of a world, and you had to do compute a path through it, and in order to solve the problem. And so Dar was suggesting we talk about, well, how would we actually write some of that in Clojure? So today I want to talk about how you would do a pathfinding in Clojure. So we're basically going, I'm going to, because it's going to talk a little bit about how to do like loop and recur. It's going to talk about how to do, just managing this little bit of state. Hopefully it'll be, if you've got an algorithms background, of course you're all going to, see that this is just, essentially we're just working into Dijkstra's algorithm. But how do you actually write that in Clojure in a reasonable way? It's not, if you haven't done it, it's a little tricky. Not tricky, but it's a little, there's some gotchas along the way. All right, so let's talk about how we're going to represent our world. So a lot of the advent of code problems, you have this 2D or 3D world, like that goblins and elves was a 2D world, right? And other ones you had, maybe a set of named nodes, or sometimes you have a set of things you have to compute to say you can go from A to B, and there's some logic that you have to compute to say, to understand how you can go from A to B to C and which ones you can go to and how much it costs. For the purposes of what we're going to do, we're going to assume that everything we have can be represented by a vector. Is this big enough, by the way?
Yeah.
Okay, cool. Can be a vector. And so this is the kind of the canonical map representation we'll all use here, which is to say you have a map with a set of nodes, and each node has a vector of all the other nodes it can get to. So this could be logically, this could be coordinates. 0, 0 can reach 1, 0 can reach 2, 0, right? Whatever representation we have, we can represent it like this, or we could write our code to use a different representation, but this is the one we're going to work on. So the reason this is very nice is we can ask some simple questions. For instance, we can actually ask if an edge exists, and if so, what is it? So you can say, what are the edges of node 1? And we get back node 2 and node 3. We can do something like go over all of the edges and print them out, right? So we can easily work with this representation. It's a very simple representation. All right. So we're gonna write this in a couple ways, and I'm gonna kind of show how I would build up into a proper pathfinding thing. Maybe just a little bit bigger. All right. So the first question we want to answer is there a path from A to B? How can we tell that? Now, this code here is about 90% of the work, right? But it's very simple, I think, to understand what's going on. And to answer this question, I'm going to do simple breadth first style traversal of the graph, and very simple. We're going to keep track of two things. We're going to keep track of all the nodes we've seen, and we're going to keep track of all the ones we haven't been to yet that we want to, all the nodes we want to get to. And we're just going to loop over this array, right? Each time we're going to take a node from the frontier. This is unvisited, right? The things we haven't gone to yet. We're going to take one out of that, and we're going to see, and basically add it to the places we've seen, and and we're going to iterate that until we get to the end, and we've answered the question of whether or not we can reach the 2 node from the from node, right? Whether we can reach B from A. So we'll go through, and we're just going to loop recur. So this is your basic loop recur. Now, again, I'm doing it this way just so that we can control the iteration, make sure we don't overflow the stack, right? And this is a very this is pretty much the only way to do it in Clojure when you're trying to iterate it. Like oftentimes we can use reduce, right, or we can do some sort of construct like that to pull things in, but in this kind of case, we don't know how many times we want to do it. We're basically just going to keep repeating this loop until we're done, right? Maintaining some state along the way. So we can call back into the function itself, or we can do a localized loop recur. All right, so every time we're going to come out and I'm just going to repeat, and I'm going to ask myself, does our scene set, have we visited the node we're trying to get to? If we have, we're going to exit out and just say, yep, we can reach it. If we can't, I'm just going to pull the first item out of the set, out of the vector of things we haven't visited, and I'm going to compute all the neighbors, which is to say, and now I'm using jumps to be our map. You'll see, Steve will appreciate. I'm actually going to use this on the EVE Online universe map in a minute. So this is jumps as in Stargate jumps in the system, because I tried to refactor the code and take out all the names that were not meaningful, but I left this in and didn't realize it until the very end, because it made sense to me, right? But if you're wondering why this is called jumps, that's really, just think of this is the edge map, right?
Steps from one cell to the next cell? Or?
Well, jumps is going to be our jump map. Particularly, this is the edges array. This is the one that has the nodes, the data structure I showed at the front. All right, it was nodes and what we can reach from it. All right, so we asked for the jumps into the next. Again, I didn't clean up my naming here. So I asked for basically I find all the neighbors, all the things we could reach from whatever node we're considering now. I remove all the ones that we've already seen, and I remove all the ones that I'm already planning to visit. And
using
then
the right thread macro,
uh,
right? So
yes. Okay, yeah.
Okay.
So remove predicate collection, right?
Okay.
So this is a set of neighbors like node A, node B, node C. I'm going to remove all the ones that are in the scene thing.
Okay.
This is again, the nice thing about using a set here is that you can use a set as a predicate, right? Okay, so if it's in the scene set, then I'm going to remove it out of this. And I'm going to also remove all the ones that are in the frontier. Why did I have to use .contains here? Because that's how you ask if something's in a vector in Clojure. We have contains with a question mark, but contains with a question mark. Okay, so here's some Clojure for you. So there's contains, and so if I come over here, contains, so let's say if we take a set, A, B, C,
can't go on set. That disappoints me.
just a second. All right. So does the set ABC contain A? Yes. Does it contain D? No. That works, right? But we can only, and we can say X1, Y1, right? Does this contain X? Sorry. Yes. Does it contain Z? Oops, sorry. Does it contain Z? No. All right. So it seems like we should be able to do something like this. Contains A, B, C. Does this contain A?
But I bet it contains 0, 1, and 2.
Yeah, it does, exactly. But does it contain 1? Yes. It contains the index 1, right? Okay, so this is the thing about contains, is it asks the question, is this key, like is this index in the in the collection? And it only answers it for things that it can answer in constant time.
What's
right?
the doc string for contains? Okay.
So for indexed collections, it's return. It's basically the way to remember what contains does is remember that contains only operates on things that it can do quickly, right? So asking if A is in a vector is only something it can do in linear time, right? And so that's not a question that contains will answer. So it basically only asks after the key. So there's actually, as far as I know, there's no Clojure function that does the equivalent of .contains.
I think the more idiomatic Clojure way to do it would be to use sum with a set containing just the one element you're looking for, if you don't want to do it.
Yeah. So originally I wrote it like that, but I find it's like trying to explain why you're trying to sum, with a predicate, and that's a chunk of code, right? So to me, this is very clear. So you're right that there are other ways you can write that in Clojure, but there's no equivalent of .contains as far as I know, right? And so this is what I want, mentally I think this is what I want. So that's why I'm using it here. But yes, there are other ones. So basically I want to remove anything that's in the frontier. So any neighbors of the current system we haven't seen and we're not already planning to visit, that's our neighbors. And then we add the system we just visited to the scene list. We add the neighbors into the frontier. But we take the subvective 1. That means take everything but the head, right? We took out element 0. We took out the first element. So we're going to take all the rest of them, and we're going to add our neighbors into it. With a vector, this is fairly efficient, but as we'll see in a minute, a vector is not really the data structure we should be using here. But it's the only like common. This is what I would write my first pass through, right? That's what I did write and that's what I'm showing you. But there's a better data structure we can use here. All right, so that's it. All we do is we keep doing that until we've gotten to our destination, right? And if there's no more things that we haven't visited that we want to visit, we'll return false, right? And that's it. That's a basic search. Loop recur works pretty well. Some trick, a little bit of Clojure you have to write to sort of manage the stuff, but mostly the data structures all make sense. All right, so now we want to. This is not really the right data structure. We're using a vector, but if you saw, I'm trying to. What am I trying to do with the vector? I'm trying to get the first thing out of it. I'm trying to pop the first thing off of it when I'm done with it, and I'm trying to put a bunch of new stuff at the end. And that's not a data structure that's vector's pretty good in Clojure because it's immutable. Subvector does what you want. It gets you. It actually does quite well in terms of performance. What we really want is a persistent queue. Clojure has a persistent queue, right? The problem is there's no literal syntax for that in Clojure. I can't put like what I'd like to
I've run into that where you're like,
I don't know, like maybe like this.
Is there a nice way to create this?
Yeah.
Why do I have?
Maybe a persistent, like we already used this already for like the difference between a map and a set. Why not do that? I don't know why they didn't do that.
I was doing something that needed it, and that was the way to you can create it like that, or you can just create the new instance of it. But there was just no nice way to get there from here.
Right. So what's a queue? The difference between a queue and a vector is a queue is going to let us. So we'll have a set of elements, and we can put things on one end and take things off the other end efficiently. What we can't do efficiently with a queue is jump into the middle of it, right? And actually, I don't actually know that in the Clojure data structure. It actually might be able to do that because that might be. I don't know how it's actually implemented, so I shouldn't say that. But there's no literal syntax. How do we get the first thing off of the queue? Peek. Standard Clojure, right? How do we get this? Take the first thing off and discard it. Pop, right? And then how do we put something into it? Well, we basically just conj it on, or do the equivalent with into, right? So let me show you how persistent queue works real quick, just so you can see it. And they've actually improved this in recent Clojures so that it's got a nice little output. So let's say if I con.
So cute.
Yeah, right. All right. So I'll conj 1, 2, 3, right? So I've got some numbers on there, and it's showing it actually as a queue, right? If I peek.
What version of Clojure are you using here?
Probably 1.9.
So that's not part of the new data 5.
This is Clojure 1.9, yes.
Okay. All right.
Yep. All right, so we peek, we get the first one, we pop, we get the last one, and then we can keep, we can add on to it. We can conj a 4 onto it, right? And we can keep going, right? So this is the data structure you want to use, right? And this is the one that fits what we're doing. So all I've done here is rewritten this using a persistent queue. I've rewritten first as peek. I've rewritten subvect as pop, and then into stays the same, and it also supports contain. So this is exactly the same thing, and it works really well. Lessons I would say are, do look at peek and pop when you know, just like we use conj, and conj has different meanings for different data structures. Peek and pop have kind of the meaning you think of for those. For a vector, by the way, what is peek of 1, 2, 3, 4? It's going to be 4, and pop 1, 2, 3. So pop, basically vectors are stacks, right? So peek and pop on a stack, right? So if you're doing that, so anyways, my point is, like, instead of using first and rest when you're doing whatever you're doing, consider using peek and pop, because they'll have the meaning, they'll do the right thing for the data structure you're using, and when you want to change your algorithm or something like that, it's going to continue. It should continue to make sense. The same way into and conj just sort of made sense here.
Is there a push, or did they leave you with conj?
Push is conj.
Okay.
So, so if we conj onto 1, 2, 3, if we conj the 4 on, right? Whereas with the persistent queue, so if we take that and then conj 4 onto it, it's going to. Well, actually, I guess in both cases they go to the right place at the end. It's just where pop is coming from. So, but yeah, there is no there's no push. All right, so peek, pop, persistent queue. Very useful structure to use. Okay, so that doesn't really. I mean, it's great to know if there is a path, but what we really want to do is know the length of it. So how do we take this the next step of actually computing that? Well, this is going to be exactly the same, almost exactly the same code, except for I'm going to go switch from using a queue to using a priority. Well, what I want is a priority queue. And Clojure doesn't really have a priority queue, but what it has is a priority map. And this priority map is in Clojure data. It was an old contrib library. And the idea of a priority queue is you put, just like in a queue, you put things in and they come in on the end, right? And you're pulling from the head and putting it on the end. When you put it into the queue, instead of going into the end, it's going to have a value associated with it, and it's going to kind of be put in the right place in the queue. So if you put something in with a priority of 5, and then put something in with a priority of 4, that 4 is not going to be at the end, it's going to be at the beginning. It's going to go one in, right? So if we use a priority map and use the priority to be the distance, how many jumps it's taken us to get to the node we're getting to. If we use that as a frontier, we can write almost the same code. We go through and we peek at the priority map to get the next node, right? So we're going to start off with our destination node at 0, and then find its neighbors, and we're going to do exactly the same work as before. And then as we put things back into the frontier, into the unvisited set, we're just going to say it's one more distance than where we've been so far. Let me show you how priority map works, though. All right, priority map. Okay, so I'm going to put something in a priority map with A of 1, right? And then, so we have to associate that, and then I'm going to put something in with a priority of 2. All right, and the order that we're seeing is, so this is a queue. We can interpret it as a queue. So A and then B, right? This is exactly the way our priority, this is the same way as our persistent queue worked. I could put C in at 10 and it's going to go on to the very end, right? But if I were to put, say, another thing in at priority 5, it's going to come in sorted. So it's basically sort of sorts it. So so this is my way of being able to put in and prioritize which node comes out. So if I peek at this, I should get A1. And if I pop that, I should get all the remaining elements, right? So I can peek off, peek. And each time I'll get the node and its priority off of the list. So that's all I'm doing here, is each time I pull off the next node. And I'm doing the same recur, so all we do is we basically visit the system, so we add the system at the distance we just got, out of the frontier, and then we have to do a little bit of work to add something into the frontier. So what does this mean? So if we're at node A, and it took us 5 steps to get here, and then we want to go to node B, which is a neighbor, it's going to take us 6 steps to get from 5 to 6, right? So let me explain this code very, very briefly. This is where I'm trying to take all of the neighbors at one more distance than I am now. So let's say A is connected to B and C. All I want to do is, what I'm trying to do is create a map here. It's saying, so if we're at A1 and we want to visit B, what we want to do is produce, or B and C, we want to visit B at 2 and C at 2, right? That's all I'm trying to do here. Zip map basically takes the names of the nodes and the distance and just constructs a map. So what I'm trying, essentially what this code is doing is zip map, the neighbors, so let's say B and C at some distance 6, right? Repeat. So that's all the zip map is doing here, right? Zip map is a very, 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 very handy Clojure structure. Obviously, this code, if you're not too, if you haven't done this, is a little bit much to just immediately grasp. But hopefully, you can get the idea. The only other thing I wanted to point out is, so again, we take all the stuff we haven't visited, pop, we add all the new things. But what if we were already planning to visit node B, and then we haven't? B is also a neighbor of something that we've seen, right? So in the previous ones, I was able to remove all the things that were already contained in the frontier. Well, that's not so easy to do here, and I was trying to think, what's the simplest possible way I can say, if I'm already planning to visit node B at distance 5, and now I'm trying to visit it at distance 7, I want it to stay distance 5. But if I was already planning to visit at distance 5, but now I can reach it at distance 3, how can I choose distance 3? So I take the existing things I'm planning to visit, the new things I'm planning to visit, and I just merge with min. So I basically say, which one has the minimum distance? Choose that. So just to show that, merge with min. All right, so if I merge with min x of 1 and 2, I'll get 1. If I merge with 2 and 1, I get 1, right? So I just want to say choose the minimum value between the two as we're merging, right? If we didn't do that and I just said merge, it always chooses the right one, right? So if I merge x1 and x2, it's going to choose x, right? And I don't want it to necessarily choose the newest one. In this case, I want it to choose the smallest one. How are we doing? Sound good? All right. All right. Okay, so that works. But what we're actually trying to do is compute the path, right? Okay, so this is where we continue to move into some Clojure stuff. So now, again, in this case, I had a priority map of a location and a distance. Now I'm going to have a priority map of a name and a map. And sorry, this isn't code formatted. And the map's going to have 2 values, a distance of 0 and a previous node, right, that tells us where we came from, right? And then I'm saying priority map with a key function of distance, which is to say, when I put in distance 1, previous, something, it's going to use the distance as the priority value, determining how to sort and how to pull those out. All of the rest of the code here is exactly the same, except for instead of sorting with min, I have to sort with the distance as the minimum key. And I'm going to skip through this just to not belabor any points. This may be the kind of thing you just have to sit down with a little bit, but I want to show you how you work into it. and this is going to return the path, right? And I want to actually show some of this to you. Well, actually, I'm going to show it to you in just a minute. So this is computing the path, but each time, the key thing here is each time, each item is just one more jump than the last one, right? So A to B to C, 1, 2, 3, 4, like that. So we really didn't need to go through all this trouble for such a simple such a simple transversal where every edge has the same value. And so what I want to show you is how you would write this if you had nodes with different weights. So in this particular case, I'll show you the map, I guess. My test data I have is the EVE Online. So EVE Online, this is a map for EVE Online. There's a huge number of solar systems. There's about 3,000 or so in different regions. Each region has various star systems, and this is how the star systems, are connected, right? And each, it's like, well, okay, one thing we want to do when we're navigating in this game is some of these star systems have lower security values than others. And so these ones with lower security values are ones that I might want to avoid, right? I might want to say, well, if the fastest way, if the only way to get from here to here is to go through here, well, I'm okay with doing that, but I'd really rather take a few extra jumps and get around. So you don't need to know anything about the game other than to know that some of these are systems I'd like to go through, and some of these are ones I'd like to avoid. So I wrote some code on here in my map, which basically says, if this is a high security system, so one I want to go through, then I'm going to say this is going to cost me 1 step. If it's a low security system, it's going to cost me 3 steps. And if it's a null security system, which we're not seeing here, but I'll show you some. Let's go out to here. So if it's one of these null security systems like this guy, it's going to cost me 7. I would rather jump through 7 high-sec systems to avoid 1 low-sec system, essentially, right? So now we have a way, so now I have a map, and I have a set of nodes with differing costs, right? So that's this jump cost here. And all I've changed in the code for this is instead of adding 1 to the length of the path, I'm keeping a cost as well as the number of jumps, and I'm adding the cost to that. And the algorithm that we wrote there works the same. And I won't go through all the minor details of what we had to change. It's all it's all pretty straightforward if you got the previous code here. So key function, it's a slightly different key function in keeping track of one more piece of data, and the merge. And instead of merging with the distance or the jumps, I'm selecting by cost, right? So priority map sorted by cost, merging the new nodes based on their cost into the priority queue. Exactly the same thing. And so what I wanted to do then is just show you some of this. And I'll post this code. That's why I'm not going to force you to sit here and keep looking at code, because some of this. Over here. Okay. So let's actually look at some of these examples here. I thought I put some down here. I guess I didn't. Okay. All right, I guess I didn't. Okay, so let's look at some of these, okay? So I will go to a system that I know well, and we'll start computing some paths and just comparing them, okay? And I have all the code here of how I got this, and I'll just show you some of it here very briefly. I basically exported the database of systems and and into some files like jumps. So this is a set of systems that you basically jumps between them, and I extracted all the security of all the systems. I wrote a quick instaparse to parse those in and get all of that. The net result is I have that here in a structure called gate map. So if I could say gate map of one of the system's names here, it will tell me all the systems that are connected to it, and I can ask,
Does that have two goals in front?
yeah. So I can ask for all the systems between two places, gate map, and it will give me the path. So this is just the jump, the simple path. So let's look at a couple of these in here. So here I am in Lone Trek. So let's say I want to, Lone Trek. So here's JITA, the system I just said here. Let's say I just wanted to go from JITA to Korama. So that should be, where are we? I lost, so JITA to Korama right here. So I should go New Caldari, Malcolm over here. So I can ask these simple questions, and then I'll show you some more complex questions. So we go from JITA to Malcolm. All right, JITA, New Caldari. Oh, I guess there was a jump I didn't see, right? Oh, I only said from here to here. So JITA, New Caldari, Malcolm. So a very simple question like that, right? But we can do actually more interesting things. So let's say I were, let's pick something over here. So let's say I'm over here in PIOC, and I wanted to get to Eleanoda. And these systems here are the ones that I was talking about, the low security systems that I like to avoid, right? And so I can go straight here, and it's going to be 1, 2, 3, 4, 5. Or I could go around 1, 2, 3, 4, 5, 6, 7, 8. I could go through 8 and only have to go through 1 low sec, right? So let's see what our pathfinding tells us there. So if I go from PIOC to what did I say? Eleanoda. Pass all my arguments. All right, so it's giving me a path, so Onaman, Kanaka, and we come back over here to the map, PIOC, Onaman, Kanaka, right? It's going to put us up here. Now, let's call the version that I wrote that tries to avoid these lower security systems. And I called this Dijkstra because this was actually the one that's closest to Dijkstra's algorithm. So it's telling me to go Eleanoda, Nani, Onanan, all the way, or Uasara, all the way to Eleanoda. So let's see if that's what it, Eleanoda, all the way to Eleanoda, all the way over here, right? So it chose the path to go around, right? Because I told you that was the shortest, it's not the shortest path, but it's the lowest cost path according to what I said.
So if I got longer, it might end. Is there a penalty for distance, or is it always just going to be security?
So let's look at the code and let's see. So the jump cost here, I've said every jump costs something, right? Okay. So I've said a high security jump costs 1.
Right.
A low security one costs 3, and anything else, a null security one costs 7. So if it was high sec, null sec, high sec, or 5 jumps around, I'm going to take 5. But if it got to 8, I'm just going to go, according to this. Now, are these good numbers? I don't know. I made them up so that they would produce interesting paths, right? So let's. Okay, so here's the longest route between 2 systems in the game. Out of curiosity, can you guess how long it is?
4 days.
It's not, well, let's find out. So here's a route planner all the way up. So this is up in Stain, going all the way down to, this is up in Branch, going all the way down to Stain, right? So let's see what our route finding makes of this one. So I will. All right, so it found a path. Let's, how big is it? It found a path of length 100. And so here we are, 3.7 going down, 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 100, right? So most likely we found the same path, but it is possible, if you had a diamond shape, right, it's possible that this particular algorithm online chose a different route than I did. I could say, for example, I don't have the code in here, but I could ask it to avoid a particular system, and it would go find a path that didn't include that. But this happens to be the longest path of the game, just to give you a size, an idea of the size of the world.
How long does it take to transit it?
Well, given that it's all, so if we look at this, all here, this is all low, almost all null security space. And I guess if you were in an interdiction nullified ship, you could pretty much go straight through safely. But even assuming you could go straight through with nobody trying to pull you up along the way, we generally factor about a minute per jump. So I guess it would take you about an hour and a half, 2 hours at your fastest to get all the way from one side to the other. But in reality, you'd have to be very careful along some of the places, and because of the players actually there slowing you down. Assuming you lived, and as fast as possible, would probably take you about
They try to jump your ship as soon as you come to the gate, or decloak from the gate.
Yeah. So. This was really fun, and I chose this domain simply because one of my side projects is that I've talked about before is a mapping program. Not for this. So this is a huge game, but in addition to this game, there's also another space that's sort of overlaid onto it, which is a systems of wormholes, and the connections change every day, right? And so as you explore, the maps, and we want to have code that will actually take the map as we know it right now, as it's changing in game, and compute paths through it. So this is why I chose this particular domain, because I want to take this code and move this into our mapping software so that we can compute fast paths through the wormhole space. Because in reality, even though this is 100 jumps away, this could be 3 jumps through the wormhole network. If you know those right 3 jumps, right? So, anyways, that's why I chose this as the goal for that. So, I'll put all this code online. I hope I hope even if you already knew the algorithms, I hope there was some new Clojure stuff in there. And if you didn't know the algorithms, I hope this is enough that if you're interested, you can sit down with the code and play with it and learn how to do it. I think it's very valuable to be able to write this yourself. However, there is something which I decided I'll talk about on a later month. There is a really great, there's Loom and Ubergraph. And once you know how to write this, Ubergraph basically gives you the ability to do these searches and pathfinding stuff. Where you are doing what you want to do is provide the data, right? You provide the graph and the search information, and it will do, Dijkstra, A*, something appropriate, and you don't have to write it. But I do think everybody should be able to, you should be able to write something like this that, even if you don't want to write it and you want to defer to actually, well-written, optimized code like this. So in a future month, I'll show off Ubergraph and how you could write this, and we can look more at how to take interesting data and find paths through it. But if you happen to have a problem where you have a graph finding problem like this, then this is a great library. This combined with Loom is a great combination. So for finding shortest path, and you'll be able to understand not just how it works, not just how to use it, but how it actually works if you know how to write it. Cool. Thanks. don't have a topic for next month, if anybody wants to volunteer,
I would do one.
excellent.
I don't know yet, but
Do something.
maybe
NOLA something topic.
maybe I would talk to Paulette and learn how to use her Naga.
Excellent. Yeah, I've never seen how it's being used on that particular project, so it would be neat. So I'm kind of curious how, what it's looking like.
And then she wrote a thing called Asami, which I said, well, why didn't you use DataScript? Whoa, I didn't know about that. No, they're very similar, kind of. So I should compare both of those and see. That's fun.
All right, and I won't have the code up tonight because I need to kind of get it all in all the samples all together. But I will have that up for anybody who wants to play with it. Cool.
No one else presenting?
No, that was just, well, we were going to have, Sam was supposed to be here with more data for the comparison stuff. We're going to play with that a little bit more, but.
I haven't talked
So
to
he may be watching. Hi, Sam. I don't know.
I sent him the link. I'm like, hey, let's here's the link. I don't think he was watching it. There's only one user, and I was like, my coworker did not get on. But we need to get them to do that screen, not that little camera, because you can't really see.
Yeah. I've never been. That's why we've never done it. We've never asked them to do it because the value of it is pretty low.
If they can do that screen instead of whoever speaking, and he says, yeah, I'm gonna need you to change something around. Like, well, that would make it cool. I use it better than see somebody in the dark talking.
Because if you can't there's almost no case where you want to see me and not the board, whoever's talking, right?
Right.
Like most of the time when they put the presenter and the slides, I'm like, could you just show me the slides, please?
Next one. Anyone else eating about the fellow?
I can stick around for a little bit if people are.
Do you know if they're doing any parking validation at all?
I don't know. Sam's always the one who kept track of that.
Talk to the people at the security desk that can do a card.
Excellent.
This security desk or upstairs?
That doesn't work. We'll talk to this in Chemical Factory. That doesn't work. I'm gonna go talk to people.
I'll try to find y'all at the over here at the restaurant shortly.
So cool. I don't know why lucky don't have a pencil part. What do you do the pencil if you don't have a slot for it? Like I don't know.
I keep mine in my pencil holder.
Oh, then there's another
With my
thing.
actual
The
pencil.
thing you guys hold.
Well, yeah,
Oh, yeah. Which one?
Eric?
not ideal, but
Right,
The
yeah.
it works.
Apple,
Since I have it anyways.
the Apple keyboard thing would be cool, but that doesn't even have a pencil slot. So it has,
Oh,
you can stick to the edge magnetically, but if you knock it off, then it's. Ah.
Sorry.
yeah.
We were at,
Yeah. Well, I'll see you around. Probably back to
That was a pretty cool topic. I like how you were able to put the game domain into it.
Yeah, I wish I had just a little bit. I I've been so busy, I didn't get a chance to put together actuals, because I think some of this, if you can visualize it a bit, and I just didn't have any way to, I was just barely able to get all of this, you know, organized, and so I always feel bad, a little neglectful when I, well, yeah, because I can see some, and obviously not everybody was following it, you know, like, if I didn't know the code, I would have had a hard time following it too,
Sure.
right?
Well, it's hard when not everyone has algorithms background too.
Yeah.
Like, but yeah, I guess the other thing you could do pretty easily would be to dump the edge map to a dot file pretty easily if you want to visualize.
That was one of the things I was looking at doing, yeah, and that's actually something that UberGraph does, right?
Yeah, sure.
You put it in and you just call the function and it generates it for you, and that's just like, man, if I just